We start because
Okay, let's
Yeah.
start. Exactly. Let's start. So, well, welcome everyone. It's really a pleasure to have here César Hidalgo. Well, you already heard a little bit about him. So he's been working a lot in complex systems. He had contribution to economic complexity, data visualization, applied artificial intelligence. He's been for many years in MIT. So he was the leader of the collective learning group there. And he was also a research fellow at Harvard Kennedy School of Government. So Cesar, it's an active member of the new network of excellence called Elias. And by expertise, he's a physicist. So he got a PhD in physics from University of Notre Dame and a bachelor in physics from Universidad Católica de Chile. So I think his talk is very interesting, and it's already looking very visual. So well, looking forward to hear your thoughts, Cesar.
Thanks, Nico. So what I'm going to do today is I'm going to tell you about a field that I helped start, more than 15 years ago, in which we have been using machine learning methods to understand questions of economic development. So I'm going to start by first telling you a little bit what this field is about, what motivates it, and what are the basic techniques. And from there, I'm going to try to move to more recent research that shows where this field is moving. But to motivate this, I'm going to use the story of someone else, which is Tom Twaits. I don't know if you have heard of this man. He's an English designer. And, late in the 2000s, he decided to embark on a project in which he was going to build a toaster from scratch. This is the toaster project. He gave a TED talk about it. It's actually quite a well-known project, because the whole point of this project was not, that he was going to build the world's best toaster. It was to illustrate that something as simple and something as cheap as a toaster, in reality, is something that requires an enormous amount of knowledge to make. Knowledge that, in some sense, was not available to him, even though he had plenty of time to do this. He had, over a year to do this. So he actually wanted to build it from scratch. And when he means from scratch, he means really from scratch. So he would go into mines to try to collect the ore that then he would need to melt to be able to produce the metal pieces and so forth. And he would try to get onto a platform in Norway to collect the oil that he would need to produce the plastic, to produce the casing. And he didn't succeed at doing that, so he had to use some recycled plastic that he had to melt and so forth. And the result of the toaster project was, a toaster that, as you can see, was not that great. Actually, he plugged it in, it lasted about like 10 seconds and wasn't able to make any good bread. And the point of this project is that things that are such inexpensive items as a toaster, which I think you can buy for 5-10 euros sometimes in a discount store, show us that the world works not because there is a few people that know a lot, but because there's a lot of people that know a little. And we can put the knowledge together through a number of institutions, such as markets, to help us produce these goods that, are inexpensive to buy, but are actually quite complex to make. And economic complexity is the study of how that knowledge comes together. Is the study of economics, not based on aggregate forms, but taking this complexity into account, taking this granularity and taking these networks into consideration. And another way of looking at this field, a more maybe pragmatic or simpler way to describe it, is to say that economic complexity is the combination of machine learning methods and economic data to understand development outcomes. And this is something that we started doing in 2006, 2007, when machine learning was not as hot as it is today. But why do we want to use machine learning? Like, economics is not short from statistical methods. Actually, they're very advanced when it comes to econometric methods to estimate causality and so forth. But the reason we want to use machine learning in this particular subfield is because the factor of productions that we use to create products, particularly knowledge, like is exemplified in the case of Tom Twaits, are highly specific, or in economic terms are non-fungible, meaning that they're not interchangeable. So you cannot change a pianist for a surgeon, even though they both have a lot of knowledge, they're both very skilled with their hands, because the knowledge that they have is not just some undifferentiated substance, it's very specific to an activity, and we need some sort of representation that takes into account this non-fungibility, that takes into account the identity of the elements involved. And machine learning in particular, like these language models, are a great example of a representation that is able to take into consideration non-fungible units. changing the word dog for the word God in a sentence can change the meaning completely, even though it is the same words, the same letters, the same length, and so forth. So you have these non-fungible units, and usually, traditionally mathematics has not been very good at dealing with non-fungible units until quite recently. So you're all familiar with, of course, ChatGPT. This is, probably the best known example of a large language model. And what I'm going to do here is I'm going to try to build a parallel between the way in which these models, work on the background and the way that economic complexity research is conceptualized and built. So the first thing that I'm going to do is, basically start with the basic idea that what these models are doing are predicting the next word in a sentence. Everybody here understands that. But what is interesting about this is that the ability to do this doesn't come from our traditional ways of representing words. So if you went to school, you probably are very familiar with these parts of speech representation of words, in which every word is classified into a verb, a noun, an adjective, or an adverb. And even though these classifications are correct and are useful, they're not very useful to construct a generative language, because verbs can have very different meanings. So in some sense, this type of classification that aggregate things can help us describe, concepts at a larger scale, but doesn't have the granularity necessary to generate, the sentences that we would use in everyday language. So there is a problem, with the use of this representation. And eventually, these advances in machine learning hinge on the development of representations that were not so aggregate, that actually were able to represent each word uniquely using this embedding. So we went beyond this part of speech type of grammar. We use embeddings in which now each word has a unique identity and meaning. And using that unique identity and meaning, we can now construct language, and they have properties. For instance, Canada is to Ottawa or Madrid is to Spain and so forth. You have semantic properties that help capture, that are captured in the distance between these embedding vectors. Great. Now, to be able to generate, these sentences, of course, we're not just looking at the previous word, we're looking at many words that preceded another word, and we have to figure out which words we pay attention to. And this is this important breakthrough from 2017 of attention is all you need. And when you're completing a sentence such as at the library, the students open their books, you have a better chance of saying books than sandwiches, because the library and students are words that are related, to the word book. So it's not just about the words that just came before, but many words before that. The problem of this is that this actually becomes a very big problem. So if we're to look at, words, let's say in a dictionary of 10,000 of them, and we're to look at pairs of words or sequences of 3 words or 4 words or 5 words. As soon as we get to, about, 20 words, we actually have a combinatorial space of around 10 to the 80, which is larger than the number of atoms in the universe. So what is amazing about, all of this to me as a physicist is that we're able to eventually develop, a model that is able to predict the next words in a sentence, using just a few billion parameters in a problem that is literally larger than in combinatorics than all of the particles that we have in the known universe. So it's a great, success in reducing the dimensionality of a really large problem by defining with a few billion parameters what by brute force would take many, many, many more of them. Now, in economics, we have a bit of a similar problem in that we also use some parts of speech type of representation of the economy. So we like to think about, products or activities in terms of being capital intensive or being labor intensive, so labor intensive, for example, they use a lot of people, or capital intensive, they use very expensive machines, or we can think of activities in terms of manufacture, agriculture, and services, like this, 3-mode classification. But this is very similar to this part of speech classification of words that I talked about. There's nothing wrong with this. This is a useful classification, but it's not good enough to be able to generate representations of the economy that take into account the granularity of the products that we see here. For instance, like wheat or an apple, they're quite different agricultural products, or an engine and a shirt are quite different as well. So if we want to get to that level of granularity, we're going to have to discover something similar to these embeddings, or something similar to what people have been doing in machine learning to represent economic systems. So just like we can count the number of words in each sentence or paragraph and their co-occurrence, to create representations of their semantic meaning, we can count the number of economic activities that are present across cities, regions, and countries to create representations of the knowledge embedded in them. So the parallel here is that we have been able to generate, text or understand text a little bit better by using the fact that words are co-occurring in paragraphs, sentences, and chapters and so forth. By the same token, the economic activities that our world is engaging are not, located at random. They actually occur in clusters, and those clusters also have a number of different scales. They sometimes are in the same neighborhood or in the same city or in the same country and so forth. And maybe we can leverage that fact. We can leverage the fact that economic activities, tend to occur in clusters to create representations similarly to what we did on the other side, similarly to what we did with words. So that is basically what economic complexity does, is uses this basic insight, of machine learning, that the meaning of words is based on the company that they keep, as was said in the 50s. But in this case, like basically the idea is that products, industries, occupations, technologies, all of these different type of activities can also be understood based on the company that they keep, the relationships that they have. And this field got started with two contributions. The first one was a paper, in Science in 2007, where we introduced the concept of relatedness for people in this field. This is basically, collaborative filtering applied to economic development. And in 2009, by developing complexity indexes that help us explain economic growth, inequality, emissions, and a number of macroeconomic outcomes. So relatedness, is the idea that, some activities tend to co-occur with others, and that can help us anticipate the activities that economy is going to enter or exit. So when we look at traditional ways of representing economic development, these were representations that do not include information about the economic structure into account, or at least not in any level of detail. So the most common representations of economic development are line charts of the GDP or GDP per capita of countries over time. But in reality, countries that have a very similar GDP per capita can be very different structurally. Some might be specialized on the production of electronics, other might be specialized, in the production of, mineral fuels and so forth. So you can connect, products based on the probability. In this case, the first thing that we did, that they were co-exported by the same countries. So here you see a part of, the product space in which audio and video recording accessories are connected to electrical resistors, electrical capacitors, broadcasting accessories, and semiconductor devices, not because of anything, that we decided, manually, but because the economies that tend to produce one of them also tend to produce the other one. And that helps us, figure out this structure, this backbone of this collaborative filtering recommender system method. So here you have now the entire network, and here we also highlight the specialization pattern of a country, in this case, Chile. So each node represents a product. Products are connected if they're likely to be co-exported. And the products that are gray are the products that Chile did not export enough in 1979 to be considered specialized. Okay? And the ones that are painted in red, in yellow, in blue are the products that Chile was specialized in. So what you can see is that the pattern of specialization of Chile, certainly, it's quite localized in a few clusters. So here there's a cluster actually that involves, some products here you have like a fishing cluster, and then here you have a product that involves our products on agriculture and so forth. But for example, in these other parts of the product space, where you have machinery, where you have chemistry, where you have electronics, basically Chile had nothing going on in 1979. And the prediction here is that if you know the activities that an economy is performing, you can anticipate the activities that they can enter in the future. So now if you look at data from 1979 to 1996, and you see these entry events, you see that there's a bunch of new products, that Chile started exporting that became specialized in after 1979, and basically in this, 17-year period, Chile entered activities that were related, that were near the activities that it was already specialized in. Down here also you see a few other activities, and there's some relatedness there as well. There's some other activities. So what you have here now is a very pragmatic way to understand what are the activities that economy might be good at or not, And this doesn't mean that economies should enter related activities. That's a whole other conversation, but that tells you where the inertia is going, where the momentum is going. It tells you, okay, if you are here, these are the ones that are more likely, that you're going to be more likely successful at. So the idea of relatedness in economic geography now, it became a very well-known concept, is to develop a measure of affinity or distance between a location and an activity. How far is Yerevan from manufacturing of aircrafts? How far is Milan from manufacturing computer chips and so forth? And the way that this gets formalized is by using recommender systems to develop those measures of distance. The original measure of distance that we developed in 2007, the relatedness density, is basically a measure of distance that you would find in a collaborative filtering paper from the mid 2000s. It's just that same type of matrix multiplication and normalization and so forth. Now, during the last decade, what happened is that this was elevated to a principle. So after 2007, when we published this first paper on the product space, then people in economic geography, innovation studies, science and technology studies, and so forth, started to publish papers, in which they would grab other data sets and would test the same hypothesis, and they would find the same result. So they would look at industries that manufacture products in the same plants, or they would look at scholars that publish publish papers in different academic fields, or cities that patent in different technology classes. And in all cases, we find that as relatedness goes up, the probability of entering the activity goes up. So you have kind of like this very regular pattern. So in 2018, we got together with a number of scholars in the field to claim that this was a general principle that was basically a statistical law of economic geography that was true across a number of different scales. So it's true for countries, it's true for regions, it's true for cities, and a number of different activities. It's true for products, it's true for research areas, it's true for technologies, and so forth. The second, contribution that helped us start this field is the idea of generating measures of economic complexity. And this is the use of dimensionality reduction techniques similar to, SVD or eigendecomposition to summarize the sophistication of productive structures. Now, here, actually, we have to be very careful because not any decomposition is going to work. What we're interested in are the compositions that actually explain a macroeconomic outcome that is outside the data that we use to create this representation. And the outcomes that we care about are, in this case, for instance, economic growth. That's the first outcome that we explain. Economic growth actually is a variable that is really hard to explain on the long run. Has been a long, quest for economists to try to explain long-term economic growth. Income inequality. And more recently, people have put a lot of effort to use economic complexity to explain, emissions. So how does this measure work? So let me first give you some intuition using an analogy, and then I'm going to go a little bit more into the mathematics of the measure. So imagine you are asked to grade an exam, that was taken by some aliens from a foreign planet, and you don't know what the questions are about, you don't know the language, but you have the answer sheet and you have the answers that they provided, So now you need to find a way to score that exam. You know which answers are correct, but you don't know how many points you need to give to each question. Maybe there's some questions that are really easy, and maybe there's some questions that are really hard. How are you going to score that exam? So one idea that you can have is, well, actually I can endogenously extract information about which questions are simpler or more difficult from the answers themselves. So if there's a question that everybody got right, that question should get very few points because that's an easy question. If there's a question that, few people got right, that might be a harder question. And if the people that got that question right are also people that got many other questions right, well, that's not only a hard question, but maybe it's a hard question that requires a lot of knowledge because it was only answered correctly by the people that answered many questions correctly and so forth. So you have kind of like these relationships that could help you endogenously determine those weights. And that's, what economic complexity in some ways does. So imagine that you want to know the knowledge K of a city C. That's the variable that you're interested in for now. And you're going to say, this is a function of the activities that are present in that city or that country, and how knowledge intense those activities are. So basically I'm saying, look, Milan is a complex economy if it makes complex things. So what does things Milan do and how complex they are? Now, how do I know which things are complex? Well, I'm going to say the complexity of an activity, is going to be a function of the cities in which it's present and how complex those cities are. Okay? So I'm going to be defining the complexity of a place based on the complexity of the activities and the complexity of an activity based on the complexity of the place. And now if I put this second equation in the first one here, I get this self-consistent equation that I need to solve, which, when I linearize it, I get, to translate it into an eigenvalue problem. So basically, I have kind of like a matrix of similarity between locations, and the eigenvectors of this matrix of similarity between locations are a measure of their complexity or the knowledge intensity that they have if we use that knowledge interpretation. Great, so that's how you define the economic complexity index. In fact, we do it using, for this function S and G, we use simple averages, and the simple averages, define this similarity matrix, which is quite interesting. And actually, we've tried so many things by now in the last, 15 years. It's not easy to get a matrix of similarity that actually works. This matrix of similarity basically is saying, look, we're looking at the similarity between two countries based on the products that they both do. So we're going to say that, let's say, Italy is similar to Spain if they make the same products, but we're going to discount the product by how ubiquitous it is, by how many other countries make it. So we're counting, more strongly rare coincidences, and we're counting less common coincidences. And we make this a stochastic matrix by normalizing by the diversity of a country. And when we do that, we get this measure of economic complexity that is actually very good at explaining economic growth, inequality, and emissions. This is not very easy. One of the reasons why this is not very easy is that because we're working with real world data, we're working with units of observation that are highly heterogeneous. So when I grab a matrix like this, here I have, let's say, countries, and here I have products, if I'm looking at a matrix mathematically, well, a matrix is a matrix and an eigenvector is an eigenvector. But when I'm looking at a matrix that is made of real data, like a row around here is a country like China or the United States with an economy of 15 to 20 trillion. It's a gigantic economy. And a country down here is Macedonia, which is, so small that it would fit within a city in the United States or China. It's like 2 million people. You can fit that 10 times in Beijing. So if we just start diagonalizing this matrix willy-nilly, we're just going to obtain measures of size. We're going to, we're not going to obtain like good measures of the complexity of these economies because basically these units of observation are very heterogeneous. The same happens if you look at the columns. One column is going to be oil with exports of trillions. Other columns are going to be products that have very little exports. So eventually what this involves is a sequence of normalizations that you need to perform to be able to get to a measure of economic complexity that actually works. If you, let's say, for example, take the matrix of exports and you take the eigenvectors of that, they do not predict growth, they do not explain inequality, they do not explain emissions. If you take the log of that, neither. If you take RCA, this is a measure of specialization. This is basically a matrix that is normalized by the rows and the columns. Now, if you take the logarithm of that, it starts to get closer, but it's still not as good. Then you binarize it to create a matrix that, has even like more controls for these differences in sizes between the units of observation. And then once you get to this matrix of similarity between activities, you get to this measure of economic complexity. So it's actually, a quite circuitous path to get there. But once you get there, you have something that works. So these are economic complexity index rankings for the year 2000, 2010, 2020. They help us show a little bit, the dynamics of our world. So you would see, for instance, that in 2000, the economy of the world had Japan on top, a lot of European economies here as well, Germany, Switzerland, Sweden. You had the United States, the UK, Finland, Austria, and so forth. Now, if we go to 2020, there's a lot of Asian economies. You have Taiwan here, you have South Korea, you have Singapore, have climbed to the top. And economies like, for example, like that of France and the UK have moved to make way to those economies. Now, this is only using trade data. Then we're going to look at estimates using other data sets. But trade data actually is quite interesting because it is internationally comparable. We do have very long time series to look at it, and it was the first one that we were able to use to test some of these outcomes. Now, here you have the economic complexity of an economy, which is a measure of, the economic structure based on its patterns of specialization. And here you have GDP per capita, which is a measure of income or, the, total output, value added produced by an economy per person. And you see there's a very good correlation between the two. But, there's also, some interesting and significant outliers, So one way to think about this diagram is that the x-axis tells you what you deserve and the y-axis tells you what you get. okay? And here, for example, these outliers here, these are countries like Australia, the UAE, Qatar, Oman, Kazakhstan, Chile. Basically, they're getting much more than they deserve, based on their export structure, because they export a lot of raw materials, So they're actually, doing much better than we would expect, because there's something else that generates a lot of money, even though the complexity is low. Countries like, India, China used to like move along this axis, because a lot of its growth historically has been explained by complexity, are countries that, are able to compete at significantly higher levels of income than the ones that they're in. So for example, China here, like the economy of China, Thailand, and Mexico are, according to this index, in terms of their export structure, competitive with the economies of Hong Kong or the Netherlands or Poland. But their income, remember that this is log scale, is much lower, so they're doomed to grow, while these economies, depend on the fluctuations of the prices of those commodities. And that's a very well-established fact by now, that economic complexity explains future economic growth. It explains way more economic growth than measures of institutions. Actually, measures of institutions tend to be insignificant once you control for economic complexity. It explains way more economic growth than measures of education, because of course, measures of education do not capture any information about the knowledge that people have. These are usually measures of the amount of time that people have spent in a schooling system, but whether they learn something or not, or what they learn, doesn't enter into account. But when you look at a measure of economic complexity, you can figure out that maybe like the engineers that live, in Germany or in Spain know much more about, for example, how to manufacture cars than the engineers that live in Uruguay or Paraguay, even though they might have the same years of schooling. Those differences are captured by the economic structure. Now, there's a lot of work that shows, that economic complexity explains future economic growth. One of the ones that I like the most is a recent paper by an economic historian called Giacomo Domini, that what he did is he digitized data from the world fairs that took place in Paris in the 19th century, So basically, he grabbed data on all of the things that were in these expos, and he reasoned that, well, if countries were bringing these products to the World Expo in Paris, it was because these were the products that they wanted to sell internationally. These were the products that they wanted, to trade. And he reconstructed the export matrix of these countries using this data, and he shows, that you can predict growth in the next century, using economic complexity, using country fixed effects, in a regression with country fixed effects with only 96 observations. So this is a very strong result. You have 96 observations. 33 of them, 33 degrees of freedom are lost to the dummies, because you have only 33 countries, and still you're explaining growth in the next century using information, about the 19th century, that was collected from these trade fairs. There's also another paper by Isabella Weber from UMass that uses a different technique to reconstruct, export matrices on the 19th century, and also finds that these patterns are extremely persistent and they can predict really long-term growth. Here, we're not looking at that decade, but a century. Now, what happened is that these measures were also extended to different geographies, different type of activities. So for example, here you have the economic complexity of cities in the United States. These are metropolitan statistical areas based on industries and payroll, and based on patents by technology class. These are actually quite interesting because they show that this is not simply like a population density story. For example, when you look at patents, Chicago sucks. It's a huge city, but doesn't do very well, because it's not so technologically sophisticated. Boise, Idaho does really well. Well, what's in Boise, Idaho? That's Micron. That's the only place in the United States that manufactures, RAM memory. You have Rochester, Minneapolis, also, small place that does really well. What's in Rochester, Minneapolis? 3M is one of the biggest companies in the world in terms of, material science. Austin, Texas does better than Houston, because it's more knowledge intense. So this is not something about size. This is actually picking, San Jose, San Francisco, Boston is picking like the innovation hubs, because they're coming directly from the structure, not from the volume. Here is economic complexity for the UK. Here you recover more or less like a standard pattern, like of course London and Oxford, and Cambridge, and Manchester do quite well, again here in Scotland, Edinburgh and Glasgow. Here you have economic complexity in China, Beijing, you have Shanghai, you have here Guangzhou, Shenzhen, doing quite well as well. This is a very different data set. This was a data set from publicly listed firms, super small data set, censored bias, but still that seems to work. Here is economic complexity in Mexico, according to the central bank estimates, according to estimates that we developed for Data Mexico. What you observe here is, this north-south divide, well known in Mexico. In Italy, you have something similar to, so Nuevo León in Mexico, very big manufacturing hub, where the city of Monterrey is located, super high sophistication. States like Guerrero here in the south, they do much more poorly, showing that this is not kind of like a single economy. This is a country that actually has enormous heterogeneity on the knowledge that exists in each one of these regions. It's a large country. Now economic complexity has also been used to explain income inequality. Here we have one of the models that we published in World Development in 2017, and the idea here is that basically we can go beyond the Kuznets curve. The Kuznets curve is the idea that inequality can be explained with the income per capita of countries as an inverse U curve. This is the idea that inequality grows and then declines as economies become more developed. But once you put economic complexity into the model, you start losing some of the significance. Now you're not down to 2 stars here on the Kuznets curve, because what we're able to do is to separate middle income countries that are resource intense, like Chile, Tunisia, Peru, Kuwait, Egypt, and so forth, that are very unequal, with middle income countries that are very similar in macroeconomic terms, when you don't consider complexity, like Malaysia, Poland, or Hungary, but are very different in terms of productive structure, and they're much lower in terms of inequality. So GDP per capita cannot separate Chile and Hungary or Malaysia very well. They're very similar. Chile, Malaysia, and Hungary are very similar in terms of GDP per capita, education, and so forth. But they're very different in terms of the productive structure, and this helps explain an important amount of international variation and income inequality. And more recently, people have been looking at greenhouse gas emissions. This is the idea that economic complexity helps explain emissions per unit of GDP. So this is the idea that as you move towards more sophisticated activities, the emissions that you produce for each unit of GDP that you generate is lower. Now, there's some limitations of some of these measures of economic complexity that we looked at before, particularly the ones that are based on trade. And the limitation is that trade, is a variable that, it comes from customs data, and it comes from physical products that actually have, very different costs to move around. So, for example, if you're manufacturing cars in Germany, you want to have Slovakia, Hungary, Austria and Czechia in your value chain. You don't want to send things, back and forth to Australia. So what happens is that trade-based measures of ECI tend to have a bias that is positive towards countries that are integrated to the value chains of their neighbors when the neighbors are sophisticated. So Mexico is doing really well because it's integrated to the value chain of the US. Czechia, Slovakia, Hungary do very well integrated to the value chain of Central Europe. And countries that are far from global markets, such as Chile, Australia, New Zealand, do poorly because for these countries, it's a better deal to export those raw materials that you can put on a ship. They're not so time sensitive. They have a lot of value that you can pack when you load each one of those ships, and they would specialize in these other activities. So one way to take this bias into account is to go beyond international trade and consider other forms of economic structural data like patents, research papers, and so forth. And that's what we did with Victor Stoikovsky and Philip Koch. We published this last year, and when you look into that, for example, if you look at technology and you look at patents, here you have Mexico, here you have Slovakia, here you have Australia. Basically the tables have turned. Now, when you look at technology, Australia does quite well, Mexico does quite poorly because Mexico is working with imported knowledge, and Australia is generating knowledge for the processes that they use to generate raw materials. Like Chile also, for example, here does much better than in economic complexity measures based on exports. When you look at research, now here you look at academic publications by research field. Here, the United States, Canada, the UK, Australia, basically all English-speaking countries do amazing, And once again, for example, Mexico is not doing so well. Central Europe doesn't do as well as they do in measures based on exports. The nice thing about this is that these differences, are complementary. So like what motivated this difference is that the ECI trade was biased in favor to countries that were integrated into the value chain of their neighbors, and biased against raw material exporters that were far from global markets. Well, now we have measures that are complementary, and when we put those measures together in the model, we actually can explain economic growth, inequality, and emissions better than before. In particular, trade and tech ECI combine to explain growth and inequality better, and emission intensities are actually best explained. The most important term is the triple interaction term, meaning that emission intensities tend to be low in countries that do well in the three measures of economic complexity, basically in trade, research, and technology. Now, what I'm going to do is I'm going to tell you a little bit about where this field is going. And I'm going to show some of the recent work that we have been doing, because what we have here is basically a field that has pioneered the use of machine learning methods in economic development, and has helped us explain and understand certain patterns of development that have been long existing, but we can now use it to look also at the past and the future in ways that we have not been able to look at before. So I'm going to show you two papers, one which is accepted for publication, and another one that got very good reviews from a very good journal recently, so probably it's going to come out later this year. The first one tries to incorporate an aspect of the economy that so far has been neglected, not only in economic complexity, but more generally, and that is trade in digital products. Okay, so when you open Netflix here in France, you're actually, consuming a product that was manufactured in California, whether it is that series and that movie, and certainly that website, And there is a lot of trade that takes place in the world right now that occurs through the web. But this trade is very hard to account, particularly when this trade belongs to what in the GATS classification is known as mode 3 of trade, which is trade that involving the creation, let's say, of a foreign subsidiary that helps re-export this product. So for instance, Netflix here in Europe operates from the Netherlands, but it's not really, like a Dutch company. It is, an American company. Similarly, Amazon operates from Luxembourg, or Facebook operates from Ireland. So what we did, we spent about a year and a half generating a data set, basically Victor did, in which we collected corporate revenue data for thousands of firms. We disaggregated our corporate revenue data by different streams of revenue, so we could have information about the different, products that they are producing, like whether it's cloud computing, video streaming, video games, and whatnot, to create a data set on digital product trade. Here you have, like a snapshot of some of this data, using a headquarters location to assign trade to a country, or the fiscal residency of the subsidiaries. So we look at the subsidiaries, for example, the EU looks quite well, but you see Amazon, you see Alphabet, you see Oracle, you see, Meta, which is Facebook, and you only see a few European companies like SAP, Bookings, and Spotify, When you look at it by headquarter location, you see that actually, digital trade is very much dominated by the United States, and China does actually quite well too, and the EU is much smaller, is, Booking, SAP, and also Spotify, as you may know. If you look at the residency, also what is interesting is you see that a lot of the Chinese internet operates in the world from the Cayman Islands. This is CYM, is Cayman Islands. So Tencent, ByteDance, Alibaba, actually have, the residence, there, but certainly this is not where the software, is being produced. That's the headquarter location. So why is digital trade important? First of all, it's, the fastest growing form of trade. So it's growing at about 25% at an annualized growth rate. So that's super fast. If you ever look at economic growth numbers, like 7% is already super fast. That means that you double every 10 years. 25%, means that you double like around 3, and a little bit less. The trade in goods is growing at about 6%, trade in services at around 4%, trade in digitally delivered services at about 8%. So these digital products, these like basically subscription type model, or productized services, is the form of digital trade that is growing the fastest among all of the form of trades that we have right now. It also has a very different geography, and network structure. So we look at digital products, you see that basically the United States is kind of like the center of the world, and then you have Ireland, the Cayman Islands, and China, as other hubs. Digitally delivered services, include many more countries. The trade of goods also has several hubs: China, United States, Germany, and so forth. It's much more interconnected. The service trade, map also, has several clusters, while the digital product trade cluster map is really almost like a hub and spoke structure. It's a very centralized, structure. On the right here, you can see, the eigenvector centrality of these different networks. And for example, the United States is very strong in digital products, but for example, China is the most central country in the exports of physical goods. Okay. It also helps us revisit trade balances. So for example, the United States or Uruguay or the UK here are countries that have a negative balance in goods and services, but have a positive balance in digital products. This is balances in per capita. So basically, let's say the US is between 1K and 10K short in terms of their goods and service trade balance, but when we incorporate the digital product trade balance, you get like one of those K back. So it helps us rethink about this trade balance. For instance, the trade balance of the US is not as negative as we might capture through other measures, because the United States is not exporting so much through physical ports, but through internet ports. And one other thing that is interesting is that digital trade is correlated with economic decoupling. This is the idea that GDP per capita or measures of wealth in a country can go up while measures of emissions go down. And there's several economies that have decoupled, like the United States, the UK are examples of economies that have decoupled, that have continued to grow while reducing emissions. And what we find is that basically decoupled economies tend to perform much better in the export of digital products than other economies. So there's a correlation between decoupling and digital product trade. And finally, it also improves, our measures of economic complexity. So countries that are good digital exporters, tend to perform better. You adjust up their economic complexity because, these digital trade products, once we append them into the physical product export matrix, we infer that they tend to be of high economic complexity compared to the average physical good. And now I'm going to turn, for the last part of the presentation, my, telescope backwards, and I'm going to use these methods not to look at the future, like digital trade, it's a growing part of trade in the future, but to look at the past, And what I'm going to do here, which is work of Philip Koch and also with Victor Stotkowski, is use, these machine learning methods to generate data on historical GDP per capita for European regions. So this is the current state of the art when it comes to data on historical GDP per capita. It's the Madison project. It's a project out of the University of Groningen in the Netherlands. And for example, you go back to the year 1300s, you have, five, estimates of the GDP per capita of the whole Europe. One for Northern Italy, one for France, one for Spain, one for England, one for Sweden, and that's it. There's no more data. And to collect this data, basically economic historians had to go into basements of churches to look at records and do whatever they could to just get those 6 data points. When you look at the year 1750, we're not doing that much better. We do have like a few more estimates. We have an estimate for Germany or for Finland or for Portugal. We have some regional estimates for Spain. But even though we are about 450 years, into the future, we have very little data. We have nothing for the United States, for instance, and so forth. So what we're going to do here is we're going to try to go from the image in the left to the image in the right, by using machine learning methods to generate estimates of the GDP per capita of a subnational European regions, And basically what we're going to be able to accomplish is to quadruple the availability of historical income data. How we're going to do this? We're going to start with data on 2 million individuals that are famous according to the Wikipedia. for which we know geocoded places of birth, death, and their occupations. So this is part of the research that we have been doing. We have been also working on collecting memory and collecting information about globally famous biographies, because that information actually tends to be very good. We don't know much maybe about we don't have too many economic records about northern Italy from the year 1300s, but we might know a lot about Renaissance artists and inventors and noblemen and so forth. And eventually, after cleaning the data, subsetting it, we get like a data set of about 500,000 famous individuals assigned to any of 50 different occupations. Why biographies might be a good proxy for a measure of economic growth? Remember, here we're not interested on anything causal, we're interested on the correlation. And this is because there might be direct ways in which these people contribute to the economy, or indirect ways in which these people are a signal of an economy being rich. So direct ways would be, for example, by generating an invention. James Watt or Johannes Gutenberg might help elevate the GDP per capita of the regions where they live. But also, regions that are rich are going to either attract talented people like artists, or they're going to be able to develop their local talent, because people are not stuck on subsistence agriculture. They can do actually things that are, let's say, more interesting with their lives. So the measure of whether a place is attracting painters that end up dying there, or whether a place is a birthplace of inventors, might be informative about the GDP per capita of those places, because this is where those things happen. So what we do is we train a regularized elastic model, and we validate it with a leave 20% out of sample, and here we have a baseline model that is also, out of sample prediction, and where most of the variation here you see is explaining levels and is based basically on different regions of the world or different time periods, But within each one of these bins, the model is unable to separate anything. And now when we use our model in which we incorporate all of these features, we get an out of sample prediction. This is our 20% out of sample of about 87% R squared, and we get like, a lot of, good information within each one of these periods, that allows us to, validate this as a measure of, income per capita or GDP per capita that we are going to then use to generate maps for each one of these locations. Here it's a little bit more about the model performance. So here, for example, we compare the R squared within a period. How well do we do at explaining GDP per capita, or predicting GDP per capita for 1400s, 1500s, and so forth. And we do much better than the baseline model as well. We have smaller errors, higher R squared and so forth. So in general, the model actually, behaves surprisingly well. Honestly, it behaved better than what I expected when we started this research project. So we then validate these estimates using a couple of different techniques. The first one is we try to reproduce some historical facts. One is this little divergence. So one thing that is, described in the qualitative literature of economic development in Europe is the idea that the south of Europe used to be richer, up to like more or less the year, let's say 1500, but the north of Europe grew, faster, between the year 1300 and the 19th century, and basically overtook in terms of income per capita, the south of Europe. And we can reproduce these estimates using this information, and we reproduce the fact, basically, the north starts poorer in our estimates, becomes richer. The south, more or less stays flat, throughout this period, reproducing this little divergence, which is something that we didn't put into the data, is something that, comes out of the model. We also use other proxies, so for example, body height, is a proxy of, well, this is body height, among people in the military. We have a correlation with that, that helps validate our indicators as well. We have, an OECD well-being indicator for the year 1850. We cannot correlate with that as well. And here we have city level church building activity. So how many cubic meters of church were built in each time period in each one of these different places. And this is important because basically, this is a measure of excess income. If you are a society in the year 1450 or the year 1400s, if you are putting a lot of hours into building a church, is because you already figure out, how to work the farms, you figure out how to work other things, and then you can dedicate, that labor force to that activity that is certainly, not productive, and it's very expensive. And we also, validate against that. So what we're able to produce is these estimates at the regional level, and we can now do like a little bit of, economic history of Europe for all of the places that we have enough data to create these estimates. So if we go back to year 1300, you see Italy was doing really well. It was, time of, Tuscany and the north of Italy, that were doing the best according to these estimates of, GDP per capita. For the year 1400, Italy continues to be kind of like the economic center, but then by the year 1500, we're going to start to see that little by little, Netherlands also is going to start to show up. By the year 1600s, we start kind of like getting like that Dutch, thrust coming in. And by the year 1700s, now, we have like basically these two centers, in northern Italy and in the Netherlands. Then when we move to year 1750, we start getting some estimates also, for the United States, and then by the year 1800, London, which is hard to see because it's very small, is doing quite well, and by the year 1850, like Paris, London are doing much better as well. We start seeing like big difference between, Eastern and Western Europe, and by the year 1900, we kind of like have estimates for almost every region in Europe, and for also many regions in the United States. Like the parts of the United States, like here in the center, are not very populated, but for the populated regions in the East and the West, we do get to provide, those estimates. So the last thing I'm going to do is I'm going to show you a little bit like how these ideas are put into practice. So what we've done over the years is we created many economic data observatories that help bring this data and these ideas, to millions of people every month. So the Observatory of Economic Complexity right now is the #1 tool in the world to visualize and distribute international trade data. We have built platforms, in Brazil, such as Data Viva. We have built platforms in Spain, in Peru, in Estonia, in a number of different countries that combine to millions of monthly users. And the example that I'm going to tell you a little bit about is Data Mexico, which is a platform that we built together with the Secretary of the Economy of Mexico, because the way that this was used was to not only provide economic data to the people of Mexico and to the people in government, but it was used by the Secretary of the Economy of Mexico to train their embassies around the world so that they could use this platform for their foreign direct investment efforts. And actually, it was a very successful pilot to try to bring, foreign direct investment to Mexico, especially at the time of COVID, which was a time in which most of these meetings were happening in remote, and they required, this type of digital content. And with that, I would like to conclude by saying that the world is certainly complex. Tom Twaits knew that when he tried to build that, toaster, and he illustrated that marvelously. And the reason why it is complex is because it is made of highly specific and non-fungible knowledge. But using this economic complexity methods, using these machine learning inspired techniques, we can actually develop representations that can help us understand the economy at that fine level of resolution and to see where they stand and where they're going. Thank you.
Wow, thank you, César. That was really fascinating. I think it's really, really nice. I love it. It looks a little. I mean, what I like about it is that it looks very much deterministic, right? So should you know all these kind of parameters and so on, you could say how a particular economy is and how it could develop, right? So somehow it's also what I like is more like a recipe. So let's say now Uganda wants to look into what's wrong with their economy. And they could start kind of playing around with some of the parameters. They know what is, let's say, their resources and so on. They could probably tell, or using your observatory, can see what they really need. Okay. One thing that I was missing a bit, maybe it is somewhere, is that many of the countries are living on tourism. And tourism is very complex in some sense, right? Because you are not producing things, you are maybe consuming, but you are bringing money in and so on. So how would this, let's say, the tourism fit into it? Let's say Greece or Spain or so on.
Yeah. So these are two questions. So for the first one, it is true that there is kind of like some sort of statistical determinism, because of course the principle of relatedness or economic complexity, they're predicting things with a certain R squared that is quite far from one, you know, but they tell you where the wind is blowing. Now what happens is, like, for instance, when you look at the example of Uganda or Angola or you know, Peru or many of these countries, is that when you see where they're going, it's not where they want to go. And that's where the policy question becomes interesting, because where they're going might be like, yes, you might be good at exporting beans, but that's not going to take you out of poverty, because you need to go beyond that. And in that strategizing is, I think, where a lot of the more interesting, you know, policy work is happening. Like, we're working with countries, you know, around the world, and some of the things that we're doing is how to optimize bets to try to escape this inertia, to escape, you know, the push of the wind. On the case of tourism, actually, we had a colleague from Vietnam, you know, present, you know, work on economic complexity and tourism a couple of weeks in my internal seminar. So I think the question comes at the right time. So on the one hand, you know, tourism in the context of Europe, you know, it ends up being like a low complexity activity, because you have to think about the type of jobs that it generates, you know, and the part of the city that it takes. So let's say Florence, if it wasn't for tourism, maybe downtown Florence, it would be full of creative people working, you know, on creative activities. And right now there's a lot of Airbnbs. There's a lot of people working on the, you know, service industry in jobs that, you know, are low paid, you know, have long hours, you know, exhausting and so forth. So tourism is a little bit like the oil of the service industry, in that is very big in volume, you know, but it's low complexity. And what these colleagues in Vietnam found is that if you're a very poor country, you know, if you have, you know, an increase in tourism, your complexity goes up. But if you're a very rich country and you have a lot of tourism, your complexity goes down, you know. So it's kind of like, it's good to have tourism if you're poor, because probably means that compared to other poor countries, you probably are safer, you probably have a lot of things going on. But if you're a very rich country, it's not good, you know, to have a lot of tourism. That's why I love Toulouse, you know. It's like living in Florence, but without the tourist, you know. And I can live downtown, and you know, like, I think it's one of the highest complexity places in France, because of the aerospace industry that locates here, that doesn't have to deal with tourism, which I agree is complicated as an issue here in Europe, especially in cities like Barcelona, Venice, Florence, Paris.
Exactly. Which of course will have, I mean, now at least in Italy, we have all this kind of let's say movements against the tourists, because people say they cannot live anymore in the center. So Venice is completely abandoned by the local people, the Laguna and so on. And then of course you said about I think tourism is also related to safety. So it's also a little bit on I mean, if you are a poor country, that is probably unlikely that it's not so safe. So then people do not want to come. So it's a bit more complex than that. Okay.
Yes.
Excellent.
Yeah.
And then since you talk about, you know, Toulouse and so on, I was curious, because in the company that you were indicating at you know, in Europe, I would have imagined that Airbus would be one of those, you know, and that would have been not only SAP and whatever, what was there?
But Airbus would not export a digital product.
Okay, sure, of course. Of course.
So Airbus is very well represented on the other data set, on the one of physical product exports.
Sure, of course. Okay, there is well, maybe George, maybe you can just ask directly the question. So George Sakadarakis. Sorry, I cannot hear your.
Nico, I think that he cannot use his microphone.
Okay. He says that he cannot use the mic.
Okay, sorry, I didn't read everything.
No, but like honestly, these methods are not based on the assumption that these are, you know, non-heavy tail distributions. In fact, you know, the data is heavy tail distribution. If you look at the distribution of trade by country or the distribution of trade by product, they satisfy a log normal distribution. So there are some normalizations, you know, and transformations that you do to make these things comparable, because they usually tend to be very heavy tail. Economic data very rarely is normally distributed. More often than not, is heavy tailed, you know. So the data also on digital product exports by country. It's going to be very heavy tail, like the United States is going to be way over there on the tail, and then a lot of countries are going to be exporting very little,
Right.
where the mass of the distribution is on the left. So, but we always welcome like new methods, we're kind of like interested on seeing how, other methods that have developed in computer science and machine learning would apply to this. And they would be used to answer some of these questions, because what I think is interesting about this field is that on the other side, the methods only become valid as long as they satisfy a question that is from outside the field, which is this, question about people working on economic growth or economic development, and what we found is that is, a step that is hard to satisfy. You can always use an embedding that explains a structure that is internal to the data that used to generate the embedding, but to generate an embedding that explains something that is completely separate, it's a little bit difficult, and there might be a lot of methods that you guys have that could be tried, and some of them might work. Yeah.
Any other question?
Thanks, George.
Well, up until somebody is coming a question. I'm just curious about applying what you presented here to other domains. So one domain that came to mind would be education. So now, if you just put into the, let's say, input, some kind of background, tradition, whatever, and the neighborhood, safety, and so on, maybe you can apply this type of things to kind of estimate, I don't know, the level of education, complexity of education in different countries or in different areas, and so on. I think it would be very interesting.
Yeah, no, like in some sense, what this relies on from a theoretical perspective, like if I were to give like a different talk, like I'm working on a book right now called The Infinite Alphabet, that is about the laws that govern the growth, diffusion, and valuation of knowledge, is that what these methods eventually are capturing is information about knowledge that includes education, but that goes beyond it, because a lot of the learning that people incur throughout their lives is learning that happens, on the job, in a specific industry and doing specific jobs, and we sometimes can get close to that. For instance, in a paper that I didn't show today, using data on the labor flows of people between industries and occupations. So we have a paper in PNAS on 2018 with Ed Glazer, Cristian Jara Figueroa, that we look at all of the formal labor economy of Brazil. It's about like 50 million people, and we know exactly where they work, meaning what industry, occupation, establishment, location, they participated in. And as they move from one company to another, we assume that they bring knowledge from their previous job to their new job.
Right.
And we use that to explain the growth of pioneer firms, of firms that are entering a new industry that was not present in a location. And we find that, for example, that industry-specific knowledge that the people carry from one, company to the next helps those companies survive, helps those companies grow. So you can capture that education, but it's not this type of formal education. It's this on-the-job learning that is captured by this work history vector. Yeah.
Okay, very nice.
Yeah.
Anybody else? Well, I could stay here and listen to you forever. Really. I mean, it's very, very, very interesting when I.
But we I guess we'll have a chance to meet them in the next Elias
I
event.
really hope so. Yes.
Yeah.
I mean, looking forward to it, because I think this is what you presented here. It's really a good tool for sustainability in general, and I think it's good that, of course, it's a complex system, so it depends. Okay, it's an approximation that depends a lot of how many things you put in and what kind of assumption you have and so on. But I think it's as best as you can get in getting a mirror or of what's going on actually in economy, in all the human society. I think it's really great.
Yeah, and the methods also are very like porous in the sense that if you get new data, you can always expand them if you get new methods. So they're expandable. It's not kind of like a very closed box in that we have been able to keep on trying new stuff, incorporating new data, incorporating new ideas, and I think that's something that is important because it keeps them open. And as more data comes along, the estimates get better and better, and you're getting closer to the truth. You never get to the truth, but like the little Churchill of Zenon's paradox.
Yes, yes, of course.
Or, sorry, no.
Talk about data. I mean, I'm just curious. Are you considering also using deep learning? Because this is now very popular. Everybody in AI uses deep learning and so on.
Yeah.
So now you are getting more data, and the more data you get, the good thing about deep learning is that can reveal some something that you would not imagine, right? So instead
Yes.
of just looking for some feature and you kind of handmade, if you want, in something, because you know there are sociological laws and so on, you could kind of discover things, and this is deep learning is good at this. Right?
So like we like for like 2.5 years we've been thinking, and I think we can use definitely help there. So let me tell you a little bit about some of the failures and some of the things that we figure out. So on the failure side, one problem that we have is that, for example, on trade data, we have a lot of data. There's hundreds of countries, thousands of products, no problem. But when it comes to growth, we have very, very few numbers. So let's say that we have, these millions of data points, but if we want to use them to explain economic growth, we have to reduce them to a vector that is going to explain 300 observations. So we have very little, let's say, data that we can train on. If we're going to use a supervised learning, it's super little on the other side, and that's a bit of a problem. The other thing,
you have zero shot or few shot type of learning, so in which you can generalize in some
exactly. Yeah, and that is hard, and I don't know how to do that. The other stuff is that the economic complexity index, if you start from the exports data and you go all the way to the index, that can be expressed as like a sequence of about like 8 matrix multiplications. That's kind of like almost like a handmade deep learning, super simple deep learning model, but it is a sequence of matrix multiplication. Some matrices are diagonals. We have figured out that. So my intuition is that if we start from there, we might kind of be starting close enough to a peak that we might be able to optimize, but I think we would definitely benefit from working with someone that has trained and developed some of these models from scratch, not even with libraries, because off the box things that we've tried, we haven't been able to get them to work.
Right.
So we're thinking about it. We suck.
Okay, well, we can discuss. I mean, you probably know Bruno here around, so we are discussing about some of these things. So we'll see.
Cool. Yes.
Okay. If there is no other questions, well, anybody?
No, everybody wants to go have tea. It's buffet time.
Probably,
yes.
Probably. Okay, César, really thank you. It's really amazing what you are doing, and I think it's really fascinating and well, excellent. I think it was very nice talk. So really,
thank you, Nico. It was a pleasure to be here.
Looking forward to meeting finally in person. So I hope so.
Thanks.
Thank you,
Bye.
guys. Thanks again. Bye. Thanks.
Bye. Thank you, everyone. Bye.
Bye.
Thank you.